Hello, this is Doug Campbell. I'm the CEO of Solid Power. We are a Colorado-based company developing the next generation of solid-state batteries for mobile power markets, electric vehicles in particular. And I'm really pleased and honored to be here to brief you on what we're doing as a company. So we were established based on some research at the University of Colorado. We've been in operation since 2014. We are an ARPA-E alum, part of the RANGE program. Starting from 2014 and extending into 2017. Today, our team headcount is in the mid-50s. Really the key cornerstone of our operations is our megawatt-hour scale roll-to-roll production line that is fully operational today and really mirrors existing lithium-ion production, both in processing steps as well as equipment. And then as of today, we are in the process right now of securing our Series B financing, of which that Series B financing would achieve really two overarching objectives. One, optimization of our megawatt-hour scale production line, taking it from its current 1 megawatt-hour capacity to 10 megawatt-hour, and then similarly scaling our electrolyte material production from today's 100 kilogram to in excess of 2,000 kilogram. To be more specific, we work exclusively in sulfide-based solid-state batteries. The reason for that is we feel they have the best blend of performance and manufacturability, performance being things like very high ionic conductivity, and then manufacturability being compatibility with existing lithium-ion manufacturing processes. The image you see in front of you really shows the two products that we manufacture at Solid Power, obviously the finished cell, and then what we believe to be the most critical material component, that being the electrolyte material. And then we're a very collaborative group. We collaborate up and down the supply chain under formal cooperations. Of course, our most notable cooperations are those with end users, in our case auto OEMs, BMW and Ford. Obviously, electric mobility is coming, and as a result, the market for energy storage is growing substantially, projected to be in excess of $500 billion by the middle part of the next decade. In parallel with that is a recognition that today's lithium-ion is starting to sort of hit its theoretical capacity limits. However, the market demand for significantly higher cell level energies has not diminished. And so as a result, the community is really starting to look at advanced chemistries, most notably the use of lithium metal as an anode. And that's really where solid state comes into play. Solid state really as a platform is an enabler for lithium metal. And so we feel that we are right in the storm of that huge market opportunity. So as I said before, we manufacture both the finished cell as well as the electrolyte material. The materials we source from our partners are things such as the cathode active material, which today we work with an NMC-based cathode active material. That is provided to us. It is a tailored cathode active material for use in our cells. Similarly, a polymer binder is also being tailored for use in our cells by an external partner. And then finally, the lithium metal anode is also tailored for us. In use today, we primarily work with a freestanding lithium foil, but we're also tracking the field of a deposited lithium product very, very closely, and we've ensured that our manufacturing line is compatible with either approach. A little bit on the competitive landscape. Here you can see there are really three leading types. In addition to the sulfides are the polymers and oxides. As I said before, the real attractive features of the sulfides are things like high ionic conductivity, high manufacturability, high thermal stability, etc. Conductivity has been one of the stumbling blocks of polymers, hence why you've seen limited use there, and really on the oxide side of things, manufacturability has been their main stumbling block. So a little bit on our cell roadmap. You can see in comparison to lithium ion on the left, with some state-of-the-art energy numbers. 2020, which is where we are today, you'll see pre-A sample there. What that means is that that is our formal sample that we've established with our auto OEM partners. That is a 20 amp hour cell that we are transitioning to production as we speak. You can see what we believe to be relatively modest cell level numbers there are our targets for 2020. We've already surpassed those at a stack level with our smaller format cells, specifically 2 amp hour. And so our goal is to replicate that in our 20 amp hour cells later this year. And then you can see how we progress through A and B sample phase. B sample would be a full design freeze as you proceed into manufacturing scale. And really there's only three design parameters that we're varying there. The obvious one, which you can see illustrated here, is the thickness of the electrolyte separator layer, and then of course cathode loading and cathode specific capacity are the other design features that we will be tailoring to really meet our targets, which again, as you can see here, are in the low to mid 400 watt-hour per kilogram and close to 1,000 watt-hour per liter with that same NMC-based cathode. One of our really strong value propositions is our manufacturing compatibility with industry standard processes. So what you can see on the left is actually a graphic showing all of the manufacturing steps in lithium ion. On the right, you can see all the manufacturing steps we also use, and then of course those that are omitted are those that we do not use or do not require. So of course in manufacturing form, we'll start with powder as the base material. We then process it as a slurry. We then coat using the same coating equipment, slit calendar using the same roll-to-roll calendaring system, and then finally in our case we do a stacked cell architecture. A few key steps that are eliminated. The obvious ones are electrolyte fill and degas. One less obvious one is formation and aging. What we have concluded is that we require no formation process, and that has a major, major financial impact. And where I'll conclude is really our roadmap. 2020 is all about building and qualifying our pre-A sample. We will do an expanded pre-A sample moving into 2021. That will be a 36 amp hour cell capacity, and then ultimately we're preparing to initiate formal A sample in early 2021 with our goal of concluding B sample by the end of 2023. At that point, it is all about production scale, C sample and beyond, and ultimately we are targeting a vehicle start of production in the 2026 to 2027 timeframe. Again, really appreciate the opportunity to brief the ARPA-E team, and I hope you're as excited as we are about the future of solid-state batteries.